Good morning. Welcome to the session preview for effect handlers and automated verification. For effect handlers, we have Sam Lindley from the University of Edinburgh, and for automated verification, we have Victor Kuchik from the POPL'24.
Hello. I'm doing the session preview for effect handlers, which is a great pleasure because I've done lots of work in this area. So I'm going to give you a very high-level motivation for why I think effect handlers are important and exciting, and then I'll go through the papers in the session briefly and tell you why you should go and see them, see all the talks. So my starting point here is effects. A nice clean model of programs is to just view them as black boxes. They just have inputs and outputs, no interaction with anything else. But in reality, we often need to interact, at least with some sort of context, the outside world, normally via some sort of runtime system or operating system. And there's lots of different things. So anything that involves any kind of interaction, whether it be with users, the outside world, or other programs. And in typical mainstream systems, effects are ad hoc and hardwired. If you often, for instance, in web applications, there's several different, in JavaScript you have several different versions of concurrency, and they all correspond to kind of different effects that have to be maintained separately. This is painful. So a solution to this problem of having all these ad hoc effects, one solution that I advocate is effect handlers. Effect handlers were introduced by Gordon Plotkin and Mattia Pretner. They introduced them building on the theory of algebraic effects. A very, very theoretical context, which is not to say that they haven't had quite a lot of practical impact. The kind of chronological development here is there's a lot of work on the theory of monads, and then Gordon, along with John Power, did a whole load of work on algebraic effects. Hand waving. The big difference in approach there between monads and algebraic effects is, at least from a programming perspective, with monads you give the implementation of your effects first, and then the interface is a kind of afterthought. With algebraic effects, it's the other way around, which has all sorts of composability advantages. Although, in fact, all of these things are very closely connected. And then effect handlers are the way you implement algebraic effects. I'll give some more idea about what that means in a minute. Crucially, they're composable, customizable, and user-defined. You can define your own effect handlers inside your programming language, and they give you a general way of accounting for things. They rely on being able to give you direct access to the context in which you're running. So, if you're familiar with things like resumable exceptions or monads or limited control, it's very similar to that. It's all about interacting with that context. And they've had a lot of practical impact. So they're built into OCaml 5 now. GitHub, I think not anymore, but for a while they were using the semantic library, the Haskell library that is built on effects. Every time you did any kind of push to GitHub, it was running effect handlers. Fundamentally relied on that. Similarly, actually, the core of React, React Fiber, is directly inspired by work on effect handlers. Blazor effects is a thing that I'm working on, adding effect handlers to WebAssembly. Another viewpoint I have is I like to see effect handlers as sort of composable, user-defined operating systems that you can plug together. I'm going to give you a little example here, because I've been talking in a very high level so far, to show how you can very easily implement simple forms of concurrency on top of effect handlers. So the starting point here, when we're programming with effect handlers, is an effect signature. Here we just have one operation called yield, and it doesn't actually take any payloads. So we're implementing a form of cooperative concurrency. And the idea is we can write programs using this interface before we've actually given it any meaning. So here I'm defining a couple of threads that are just printing something out and then yielding. So we're going to interleave them, and we should see that the prints are interleaved appropriately once we've defined an appropriate handler. At this stage, this program has no particular meaning. Yield is abstract. Without the break effects, we'd actually define equations about these that would characterize how it's supposed to behave. But in the practical uses of effect handlers, the equations have often been discarded. And I think there's work to be done there to sort of bring the theory and practice back together. So here's our little handler. It's taking a list of threads, and this is what a handler looks like. It's a bit like, it's basically a generalization of an exception handler. You run the first thread, and then there are two clauses. The first one, the return clause, says what to do if you finish computing. And what's it doing here? It's just recursing. That thread we were running is finished, T is finished. The more interesting one is how you handle operations. And this is like what you would do with an exception handler, except as well as binding the effect, like generalized exception, you also bind the continuation, the context in which you're running. And this is going to be, yes, the continuation of the thread we were already running. And what do we do here? Well, we just stick it on the end of our list in the queue. So if we now run cooperate on a list of these threads, then it interleaves as you expect. So that's a simple example of effect handlers. Right, now I'm going to try and persuade you that you should go to this session. It's very exciting. You should mark all of the stars in your program to indicate that you want to go there. This is this afternoon, just after lunch, I believe. I have to admit that I am the co-author of the first paper. And it's a distinguished paper. Okay, so I'll just say a little bit about each of these papers then. So the first one is called Soundly Handling Linearity, by these authors. And it's about combining multi-shot handlers with linearity. The example I showed you before, the continuation was only used once, but you can actually use continuations multiple times, which is great for doing things like backgrounding or probabilistic programming. But what happens if you combine multi-shot with linearity? The problem is that linear type systems don't typically set up in such a way that they assume the continuation is only going to run once. And that obviously leads to problems. So in this work, we introduce this notion of control flow linearity, which restores type soundness by tracking the linearity of the continuations as well, making sure that if there are any linear resources captured there, then you cannot duplicate that continuation or throw it away, which is what an exception handler would do. A little interesting fact there is that it turns out you have a kind of duality between value linearity and control flow linearity. If you're interested in that, then come along to Wenhouse Door. The next paper in the session is on answer refinement modification. So here, this is a combination of handlers with refinement types. By adding an analog of answer type modification that you get with delimited continuations to effect handlers. Come to the talk to understand more about what that means. It turns out that actually you don't need full answer type modification much of the time, you just need to modify the refinements. To give you an example of why this is useful, it allows you to statically guarantee, for instance, that you can only read from an open file. So you have a much more refined notion of operations here. The third talk in the session is combining effects with contracts. There's work on doing this already, but the goal here is to combine arbitrary effects with contracts. So contracts are dynamically verifying properties of programs. And the actual solution is they use effect handlers. It works out very nicely. Fun fact here is that Matthias actually invented a form of effect handlers in the 90s called extensible denotational language specifications. And Cameron told me it was a bit of a fight to get him to actually use effect handlers here, but it worked very nicely. The final talk is on combining algebraic effects with OR logic in cubical Agda. So there's an implementation of effects in cubical Agda which exploits the quotient types in Agda to encode equations, which is quite nice. It turns out that it's sometimes a bit tedious to work with the equations directly. So they have a very general way of generating a Hoare logic from any algebraic theory. So this is really nice. It's embedded in Agda. And I've easily taken up my time. So here's the summary of that schedule. I think we should move on to the next session preview. We don't have time for questions.